Fantastic. Okay. Good afternoon, everybody. It is my pleasure to introduce today's speaker, Dr. Poulami Mondal. She's done her PhD in Calcutta in India and is now a postdoc. And I just heard that she's going for her second postdoc to the Tata Institute in India. And I'm very happy that she's agreed to give a talk for us today on her recent research. The floor is yours, Poulami.
Thank you very much. I would like to thank Venus for accepting my request for presenting a work there, and thank you very much for all of you to join and for this talk. So the title of my talk says Landscape of Higgs Triplet Models in Light of the Latest LHC Data. So this talk is based on these three of my publications with my supervisor, Professor Anirban Kundu, my collaborator, Professor Palash Pal, my postdoc mentor, Dr. Devtosh Chaudhary, and one of a PhD student in our group, Subrata Samarth. So let's start. So we all know that the standard model is a very successful framework to explain most experimental observations. As you can see from this ATLAS plot, that the standard the coupling modifiers are very much close to the standard model predictions. But still, there are major shortcomings from the standard model, as we all know, which are the baryon asymmetry of the universe or the neutrino mass generation or the origin of the dark matter. So all of us kind of agree that we need to extend the standard model and we have to construct new physics models. But one major motivation is also coming from the fact that the origin of the electroweak symmetry rating is unknown. So we do not know that the origin of the electroweak wave is coming from another doublet, or it is coming from even higher order multiplets, like triplets also. So so this kind of gives the motivation to look into the scalar extension of the standard model. So as you all know, a very famous, well-known scalar extension of the standard model is the 2 Higgs doublet model, which is very much well studied. But I would like to say that these 2 HDM models cannot explain the neutrino oscillation, and also if you stay in the 2 HDM model, you the kappa V, which is the coupling modifier to the standard model Higgs going to vector boson pairs, is less than 1. And interestingly, this ATLAS plot, this is the same plot from the Nature 2022 publication. It shows that the kappa V is out of the 1 sigma boundary of the standard model prediction. So this is giving us the motivation to look into the models which can give kappa V greater than 1. So here comes the Higgs triplet model. Because of the presence of a doubly charged scalar in the theory, we can have actually kappa V greater than 1 as well as kappa V less than 1, and which was not there in the 2 HDMs. And also in the Higgs triplet models, the vacuum structure is much more rich compared to the 2 HDM scenarios. So it can have like interesting phenomenology for the electric phase transition scenarios, and also Higgs triplet models can explain neutrino oscillation via type 2 mechanism. So giving by giving these motivations, I will go towards the Higgs triplet model. So looking more towards the Higgs triplet models. Now I will start talking about the Higgs triplet model type. Yes.
Yeah, can I? Are you? What was KV in that expression? I didn't.
KV is the Higgs coupling, standard model Higgs coupling to vector boson pairs, normalized to the standard model prediction.
And what is the standard model?
Is the,
okay, yeah, I have you.
Yeah. The coupling, the ratio of the standard model prediction. So the custodial symmetry says that the rho parameter, which is defined by the MW mass divided by the mg square cos square theta w, is the Weinberg angle. At 3 level, this rho parameter is equal to 1. Now, why do you want to look into the models which has custodial symmetry? Because we know from the experiment that the rho parameter is very close to 1. So you'd always like to construct a model which actually satisfies rho equal to 1 at 3 level, so that when we include higher order corrections, your model will not be excluded. So in that 2 Higgs doublet model, just like the standard model, it preserves rho equal to 1 at 3 level naturally. But it turns out that for the triplet extensions, one real triplet with hypercharge 0 and 1 complex triplet with hypercharge 1 along with the standard model doublet in order to get custodial symmetry or rho equal to 1. How? After the electroweak symmetry breaking, this Higgs doublet will gain a wave V5, and this is the real triplet which gains a wave Vzi, and this is the complex triplet which is Vk. So in order to get rho equal to 1 at tree level, we have to have Vk equal to Vzi. That is, the waves should be equal for both the real and complex triplet. So this is the kind of arrangement to get custodial symmetry for the Higgs triplet extensions. Now, in 1985, Georgi-Machacek, they came with this well-known and very famous Georgi-Machacek model, which actually preserves rho equal to 1 at tree level. So how they came up with this model? They have constructed a potential. This is the potential which is SU2 across SU2 symmetry. And by imposing that symmetry on the potential, automatically this has one solution for the waves, which is Vk equal to Vz, which is also aligned. So by construction, this model actually preserves custodial symmetry at the tree level. So this is from then on onwards, this model is very much well known and studied, and it has many interesting collider signatures. So when we look into this Georgi-Machacek model, we thought that is there any other possibility we can get rho equal to 1 at tree level without imposing the SU2 plus SU2 symmetry? So what we did was we write down the general potential with the one Higgs doublet, one real triplet, and one complex triplet. So this is the most general potential one can write. So this is the doublet structure, this is the complex triplet chi, and this chi is the real triplet. So again, after electroweak symmetry breaking, I am giving these waves to this doublet and triplets as V5, Vj, and Vk. Now, if you write down the rho parameter in terms of, as I already shown, in terms of Vj, Vk, and V5, you can see that at rho equal to 1, we need to have Vk equal to Vj. So what we did was we minimize this potential and put Vk and Vj on the minimization equations. By doing that, we get 4 constants on the scalar potential. So by putting these 4 constants on the scalar potential, you will secure Vk and Vj, and as well as the custodial symmetry at the tree level. So this is the model we came up with, which we call the extended Georgi-Machacek model. But like we at that time we name it that way, but this is not basically extension of the Georgi-Machacek model. This is a general approach to write down a minimal model, Higgs triplet model that preserves custodial symmetry at the tree level, and we name it the extended Georgi-Machacek model. Now, what is the default? Yes.
Can you remind me? Oh, well, I guess you've got it. So in the Georgi-Machacek model, you have a complex singlet and a real singlet.
Yes.
Right? Okay.
Yes, complex triplet and the real triplet. And the field structure are the same, but here we write it in terms of SU2 across SU2 symmetry. So these doublet and triplets are written in terms of a bi-doublet and bi-triplet formalism.
Yeah, I just wanted to ask, so the extended version has also singlets?
No. The exact same field structure, one doublet, one complex triplet, and one real triplet. The field structure are the same. But we are not, the only difference is we are not imposing that SU2 across SU2 symmetry.
I see. Okay, thank you. Yeah.
So the difference between the Georgi-Machacek model and the extended Georgi-Machacek model, which was our model, in the GM model, the waves maintained by the Higgs potential. And by construction of the Higgs potential, the equality of waves maintained automatically. But in the extended Georgi-Machacek model, the equality of waves maintained by tuning the potential parameters at tree level. You write down the minimization equations, you put Vk equal to Vj there, and from that you will get some coupling relations which will lead you to the rho equal to 1 scenario. So as I told that the GM model demands SU2 plus SU2 symmetry at the tree level at the potential, but in the extended Georgi-Machacek model, we do not demand that symmetry.
So that means your R value goes away from 1 at loop level.
Yeah, both of the cases, the rho parameter will.
But in the Georgi-Machacek model, if it is symmetry protected, it shouldn't go away from 1.
No, but that is the tree level. That is you are tuning that at the tree level. But the moment you go from tree level to loop corrections, your rho parameter will not be 1 anymore.
Even when it is symmetry protected.
Sorry?
even when it is symmetry protected in the
At the tree level, you impose the symmetry at the tree level. So
sure. Yeah, no, I know, but usually, yeah, I guess custodial symmetry has its yeah.
no, interestingly, actually, this rho parameter, like the T parameter, blows up in the Georgi-Machacek model when you incorporate the loop corrections. So this is only tuning at the tree level. So in both these models, in the extended Georgi-Machacek model and the Georgi-Machacek model, we have the same number of physical parameters. So we have 3 CP even Higgs, 1 CP odd Higgs A0, and these 2 singly charged Higgs and 1 doubly charged Higgs. So the physical scalars are the same for both the models. But in the Georgi-Machacek model, because of this SO2 across SO2 symmetry on the potential, these forms a triplet under the custodial SO2, and these are mass degenerate. As well as these 3 candidates, these actually 5 candidates with the F minus minus and the F minus, this actually forms a 5-plate structure under custodial SO2, and this is also mass degenerate. So in the extended Georgi-Machacek model, we do not have this mass degeneracy. So this is one major difference. Now, in the Georgi-Machacek model, if we look into the scenario that where do you stand in the Georgi-Machacek model, there are smoking and signatures in the Georgi-Machacek model. For example, the standard model is going to WWZZ pairs, which could be greater than 1, as I already told. And the standard model is going to gamma gamma Z gamma D, of course, will be modified because of the singly charged and doubly charged particles in the loop. And the doubly charged is equal to W plus could be a signature to loop, and also this H plus going to W plus Z is a signature of the Georgi-Machacek model, the Higgs triplet models, which was not there in the 2 HCM case. So these are the smoking and signatures of the Georgi-Machacek model. Now, when you revisit the Georgi-Machacek model, so from a phenomenologist, our aim was to guide experiments to look for new physics signatures. So to do that, we have to pinpoint the parameter space. So in order to
jumping again.
Yes.
I'm so sorry. So this H plus to W plus Z not allowed in the doublet extension because I would think it's CP violating.
Because actually from the H plus going to W plus gamma is a kind of vertex that is not present in the Higgs doublet model as well as the Higgs triplet models. But whether this H plus going to W plus Z is present or not, that actually depends on your multiplet structure. So you can write down this coupling. For example, you define a parameter xi of this coupling. You can write this xi parameter in terms of the hypercharge of your multiplet. So you can tune your hypercharge in such a way that this thing is 0 or non-zero. So it turns out that for the 2 Higgs doublet model, when you have hypercharge half, this coupling is 0. So this is a unique coupling which depends on the multiplet structure, unlike the H plus going to W plus gamma, which is always 0 from the Lorentz structure.
Yeah, and
from the gauge impedance actually. Yeah.
I see. You're probably going to talk about, but do you mind going back to the potential? I want to see if CP violation is allowed.
CP violation is allowed in the extended Georgi-Machacek model because you can have a CP violating phase.
Yeah.
But in the Georgi-Machacek model, it turns out that the V current equal to Vgi, which you are giving to the neutral components of your potential of the field. Sorry, the neutral component of the field is the only feasible vacuum structure. So this is the only structure. So in the Georgi-Machacek model, you cannot have CP violation on its own.
Yeah, thank you.
But in the extended Georgi-Machacek model, you can have actually.
Yeah, thank you.
That could lead you to the electric radiogenesis or things like that.
And definitely it's smoking gun signatures.
Yeah. So we want to revisit the Georgi-Machacek model, and we want to study pinpoint the parameter space. So to do that, we want to study precise theory constraint like the NA unitarity bound or the bounded from below constraints more like precisely, and also incorporate latest LHC data like Higgs signal strength, DSM Higgs searches, and also I forgot to mention flavor physics constraints as well. So then only when we incorporate all these constraints, theory constraints and experimental constraints, and find out the parameter space that are allowed from the current experimental theory, then we can propose maybe new such statistics to look for these signals. So now what is the motivation to go for the extended Georgi-Machacek model? One interesting thing is that for the Georgi-Machacek model, since the CP or scalar is degenerate with the singly charged scalars, and from the left bound we know that singly charged scalars mass can be as low as 80 GeV. So you cannot have low CP odd in the Georgi-Machacek model, but in the extended Georgi-Machacek model there is no mass degeneracy. So you can have actually low CP odd scalars, so which you can look for. Also, in the Georgi-Machacek model, in the Georgi-Machacek model, the triplet, which was the triplet under the SU2 custodial SU2, that was gauge Felix. So which can become to gauge boson pairs. So which was degenerate, but in the extended Georgi-Machacek model, there could be non-degenerate gauge Felix state, which is signatures. And also, as I mentioned, like multiple times, that there are no mass degeneracy. So one can actually expect decay between each multiplet. So one 5-plate can decay into the members of the 5 plates. So these neutral can decay into the singly charged, which are in the same multiplet. And similarly, the doubly charged scalar can decay into singly charged scalar. So these are all new decay modes which are not present in the Georgi-Machacek model. So this could be interesting to look for. Now, the question first you will ask is that how much is the mass difference, which was mass degenerate in the GM model. Now we are getting mass splitting, but how large the mass splitting can be? So in order to answer that, we are planning to do. We have done the global fit, because in the extended Georgi-Machacek model as well as the Georgi-Machacek model, there is a large number of parameters, and we see that the random scan is very much like time consuming and CPU intensive. So we have done a global fit of these two models using the code head fit. And so basically we have set our priors, and the theory constraint and the experimental constraints we put there. And from that, the head fit actually calculates the likelihood from the Bayesian fit framework, and from that, by using the MCMC algorithm, it actually samples the posterior. So finally, we need to look into the posterior by putting all the theory and experimental constraints. So this was our numerical framework. Now the theory constraints we looked for is first of all, the Higgs potential must be bounded from below, and of course the UCA and quartic couplings need to be in the perturbative region. And also the eigenvalues of the S matrix, so the 2 unitarity should satisfy NL unitarity bound. So before that, for the Georgi-Machacek model, there was 3-level unitarity bound, but for the Georgi-Machacek model as well as the extended Georgi-Machacek model, we looked into the NL unitarity bound as well. And of course, the NLO correction to the LO eigenvalue should be smaller because we are in the perturbative region. So these are the theory constraints we impose. Now, first I would like to talk about the bounded from below constraints. So the bounded from below constraints tells you that you have to make sure the scalar potential must be bounded from below any direction of the field space. So basically in the potential, you write down the quartic, if you have quartic coupling parameters in your potential, so you actually write down that part and you demand that that should be greater than 0 in any direction of the field space. Now, if we have a rich field structure in your model, then what you do is you actually, mostly people who are done is that they take at a time 2 non-zero field directions or maybe 3 non-zero field directions and compute the bounded from below constraints. When you have more than you have multiple field directions. So we did the same thing first for the Georgi-Machacek model and extended Georgi-Machacek model. We did compare the 2 non-zero field direction bounded from below constraints with the 3 non-zero field direction, and finally we computed the all 30 non-zero Bayesian field directions. Because you see, you have like one doublet which has 4 fields, one complex triplet which has 6 plus 4, 10, and you have one real triplet which has 3 field directions. So all together you have 13 non-Bayesian field directions. So we took all 13 non-zero field directions and we calculated the bounded from below constraints, and we try to see that how much that varied from each other. So you can see from the potential parameter space that the 2 field direction space, which is denoted in the gray region, this is greater than the positivity condition with 3 field directions. And interestingly, you see that for our cases, the positivity with 13 field direction and the 3 field direction, these actually generate a large overlapping parameter space. So for our cases, it was sufficient to calculate 3 non-zero field direction bounded from below, and which was much more like calculation. The calculation got much more easier by doing. Yes.
Questions.
Yes.
So I see your lambdas and kappas are going to quite large values, around 4. Is this still?
No, this is just comparison of the bounded from below constraints. We have not put anything here. Like this is just to compare how bounded from below constraints taking 2 field direction or 3 field directions vary.
Okay, and then
so you can see. Yes.
I have is that this is just checked at tree level. Is that right? The bounded.
Yes. Yes.
Okay.
Tree level. So you can see that if you can compute 2 field direction, which most of the time, like for like simpler calculation, people do to calculate 2 field directions, but it turns out that if you calculate 3 field direction, you get much more constraint parameters. And also interestingly, you do not need to actually calculate 13 field directions in this case, because when you look into the parameter space, you can see that these two are giving comparably like same allowed parameter space. So from now on, when you talk about bounded from below constraint, we only talk about bounded from below constraint with 3 non-vanishing field directions. And they will calculate unitarity constraints. So as you all know, prior to Higgs discovery, unitarity bounds at tree level actually predict the mass of the upper bound of the Higgs boson mass, and the lambda, which is the Higgs quartic coupling, which was Lee, Quigley, and Thacker calculated the bound to be less than 8 pi by 3. And when these people calculated the one-loop correction to the quartic coupling, unitarity constraints of the quartic coupling, it actually gets much more constraints from the tree level one. And interestingly, when they calculate two-loop calculation, they show that this two-loop calculation actually shows no diffusion limit from compared with the one-loop calculation. So as long as you are in a weakly interacting scenario. So because you are in the perturbative region, so your two-loop calculation cannot give like much correction to the one-loop one. But you see that the tree level and the one-loop has a sufficient difference, because when you look into the S matrix unitarity condition, which is the S stagger S equal to 1, you write down the unitarity conditions in terms of this equation, where this is the eigenvalue of the 2 to 2 scattering matrix, and this is the eigenvalue of the 2 to k scattering matrix. Now, when you calculate this unitarity at high energy, you kind of you actually neglect the k greater than 2 scenarios, which is the 2 to 2 many body scattering. So if we neglect it, and if you set L equal to 0 partial waves, which is the most contributing when you are in a high energy limit, you will stay with this equation only, which is L 2 to 2 minus half I mod square equal to 1 over 4. Your second term will go to 0. Now if you stay in a tree level situation, these eigenvalues are real. So you can come up this equation, which is real alien less or equal half, from the tree level calculation. But when you actually go from tree level to one loop, you can actually access this full unitarity circle. And that is the reason actually when you go from one tree level to one loop, your unitarity constraint get like a significant amount of constraint. But when you go from one loop to beyond, because of the perturbative region, you do not see much more modifications there. So this was the motivation to look into the one loop structure of the one loop unitarity condition of the Georgi-Machacek model, which was not done in the literature. But as we know that in the 2H tablet model, people actually calculated this one loop unitarity, and they see a much difference compared to the LO unitarity. So we did the same for the Georgi-Machacek model, and we calculated the Georgi-Machacek model unitarity conditions in the Goldstone-boson equivalence theorem, which says that when you are in a high energy, you can actually replace your gauge bosons in terms of the Goldstone bosons of your theorem. So that actually make your calculation much more simpler. So at the tree level, you can see that you can actually write all these 2 to 2 scattering states in terms of your total charge and the hypercharge. So these actually form some block diagonal structure in the tree level. So what we do, you actually, this is like 1, 2, 3, 4, 5, 6, 7. So at q equal to 0, y equal to 0, you compute a 7 cross 7 matrix, you calculate the eigenvalues. For q equal to 0, y equal to half, this is your 4 cross 4 structure and so on. This is a tree level LHC, but of course, when you go from tree level to 1 to all these structure mix up, so you have to write all possible 2 to 2 scenarios and you have to calculate the eigenvalues. So if you stay at the tree level, these are the tree level unitarity conditions for the eigenvalues, and you can see that I have shown you the block diagonal form for the q equal to 0, 1, 2, 3, 4. So if you calculate the eigenvalues by computing that matrices, you can see you have 16, 15, 11, 3 and 1 unique tree level eigenvalues. And from them, for the extended Georgi-Machacek model, 19 eigenvalues are independent, and for the GM model, 9 eigenvalues are independent. For the GM model, this matches with the tree level calculation for the literature, and for the extended Georgi-Machacek model, we computed for the first time. Now we calculate for the first time the NLU unitarity constant for both the models. So the prescription actually is the same as the Greenstein, Murphy, and they shown, and later Choudhury and Otto, they have show the NLU unitarity constraints on the parameter space. So from taking the motivation from them, we actually calculated the 2 to 2 scattering processes for at 1 loop. For in the loop, you have like all the 2 to 2 two particle states can come, and this is the perturbative unitarity constant where you demand that the NLO correction should be less than the LO plus NLO correction, or at some cases you just demand that the NLO correction should be less than the LO contribution because you are in perturbative region. And it turns out that if you calculate it, you can see that at the 1 loop level, the scattering matrix element can be written in terms of this expression, where your A0 is the 1 loop scattering matrix element, and your B0 is the 3 level scattering matrix element, and this beta B0 actually is a beta function, which in the B0 expression, at the 3 level expression, you have like, if you have 2 couplings lambda 1 and lambda 2, your beta B0 will have these 2 beta lambda 1 and beta lambda 2. So by following this expression, you actually write down all the 1 loop amplitudes, and then you construct the scattering matrix and calculate these eigenvalues numerically, and then you set the unitarity condition, which was this on that eigenvalues. So this was the NLU unitarity calculation. But when you compare this unitarity bounds and quartic couplings for GM model and the extended Georgi-Machacek model, so we compared the LO unitarity at MZ scale, which was there in the literature. Then we calculate LO unitarity at higher scale at about 1 TeV scale. Now, why we did that so? Because as you see, we have used the Gauss-Jefferson equivalence theorem, where we calculate unitarity conditions at a high energy, which is greater than the MZ scale. And there only we can actually replace the gauge bosons with the Goldstone bosons. But in the literature, actually, you see that there are calculations where people use LO unitarity, but they do that at the MZ scale. But we thought that is not something one should do. One should actually calculate LO unitarity at some scale which is greater than MZ scale. So by doing that, you can see that your parameter space get much more constant. You go from the green region to the red region by doing just LO unitarity but some higher scale. And then on top of that, we can of course put NLO unitarity conditions, and we go from the red to the blue region. And finally, we see the impact of the NLO unitarity plus perturbativity condition. And the final parameter space is shown in the brown color. So this is for the case for the Georgi-Machacek model, and similarly we do the same for the extended Georgi-Machacek model. So we see that the parameter space gets much more constant when you calculate the NLO unitarity and perturbative NLO unitarity compared to the LO unitarity. So then we try. Yes. Sorry
to interrupt you. Just can you? I'm having difficulty keeping up with with all the parameters. Can you remind me? Can you remind me what the set of parameters were? Lambda 1,
yes,
2,
yes,
4 were.
Yes, yes.
Just
in
so.
Yeah. In the Georgi-Machacek model, for the left panel, this lambda 1, lambda 2, lambda 3, lambda 4, lambda 5 all at the quartic parameters. Because we calculate the unitarity bounds on the.
Maybe you could go back and just show us the potential one more time with those.
Yeah, sure.
Just to help me.
Yes. Yes.
Okay.
Yes.
So lambda 3, lambda 4, okay. Because you were considering a wide range of even negative values for lambda 4 and lambda 5.
Yes. Yes.
Which can be dangerous. So, okay, I see what those parameters are. Those are the ones that I should look for. And the other one then,
These are the trilinear parameters, this mu1 and mu2.
yes, I see the ones for that where you had your second model with the vector.
The second model is this one. Sorry.
Yes, the parameters in that, just so I can see them again.
This one. Yeah. These are the quartic parameters, so lambda 5, lambda j, lambda.
Yes, they're more intuitive because I can see the labels on them are connected with phi and chi. Okay.
Yes. And also the kappa 1, kappa 2, kappa 3. These are also the quartic parameters.
Right. Okay.
Yeah.
All right, thank you.
So we take the prior first, and then we compute when you calculate this in a unitarity constraints on these parameters, the bounded from below constraints with 3 non-vanishing field direction are already imposed. So imposing bounded from below constraints and unitarity constraints, this is the allowed parameter space we are left with. This is regarding your question, why we have the negative region.
Yeah, no, I was concerned more about the negative values of some of those parameters, whether they're becoming squeezed. I see, going from the leading order to the next to leading order.
Yes.
And not all of them. Lambda 4.
No, not all of them.
Lambda 4 is almost becoming forced to be positive.
Yes.
So is that a trend you expect to happen? If I went to all orders, would I expect that lambda 4 would have to be positive, for instance?
And actually, if you see that in the 1 loop order, you can see that I already told that if you go into 2 loop or 3 loop, you do not expect much modification from 1 loop.
Well, it's a small modification to force it to be positive.
Yeah.
It just.
Otherwise, it's hard to tell from the unitarity.
There are several ones like lambda phi psi. These can only go a little bit negative. So I'm just thinking renormalization, group effects, and overlapping divergences and things like that can force.
No, but we already imposed 2 loop RG running of this.
Okay. All right. Thank you.
So yeah, so these beta functions are calculated at 2 loop order actually. Then we calculated the unitarity condition. So this is the parameter space for the quartic couplings in GM and AGM model. And then we look into the experimental constraints. So first we talk about the Higgs signal strength for the full run-through data. So what we fit in our analysis is the signal strength, which is basically the ratio of the production time branching ratio with the standard model prediction. So if you write down this production time branching ratio with respect to the standard model prediction, which is the signal strength, it comes out to be an expression in terms of the kappa parameters, which is basically the ratio of your Higgs going to some standard model like parameters with respect to the standard model prediction. So this is the kappa parameter. So you can write your mu in terms of the kappa parameters, and if you calculate these kappa parameters in staying in your Georgi-Machacek or extended Georgi-Machacek model, this is actually in terms of the alpha, which is the mixing parameter between the standard model Higgs, and this is your beta is basically the ratio of the weights of the triplet and doublet weight. So your kappa parameter has nothing but the mixing angle and the triplet weight. So this is the full, yes.
Did you say alpha is the mixing of who with the Higgs?
The standard model and the other CP, other singlet, other CP even Higgs, which is custodial singlet. So in the standard model, in the 2 Higgs tablet model, the light Higgs and the heavy Higgs. So here also we have a mixing like that. And so what I think, yes.
You are not taking into account fermion fluctuations. You are just considering the Higgs sector. this extended
Yes,
sector.
yes,
Okay,
yes,
so
yes.
okay,
Yes.
just for my for clarity.
Just looking at the Higgs singlet strength. So this is the ATLAS and CMS table we have used in our analysis. So we actually take all these individual signal strength numbers from the experimental papers with their correlations, and we make each of these observables in our global fit framework, and we actually fitted all these Higgs signal strength. So this is the full ATLAS and CMS table. And when we did so, we actually looked into the what is the allowed parameter space in the alpha versus V delta plane, which is the triplet wave, and this is the mixing angle. This is for the Georgi-Machacek model and extended Georgi-Machacek model. We have just written Higgs triplet in terms of V chi, the triplet wave in terms of V chi, and this is the mixing angle for the extended Georgi-Machacek model. So you see that this is the different colored regions at the constant from the signal strength for different decay modes, and combining all Higgs signal strength all together, we are in the gray region, which is the combined allowed region. And you see that at a 2 sigma level, this mod alpha cannot be greater than 0.45, and this V delta has to be less than 30 G. So you see this is coming from this gray region. And you can see that the kappa V, as I already told, that the kappa parameter can be greater than 1 in the Georgi-Machacek model or extended Georgi-Machacek model, but from the Higgs signal strength, you can see that it cannot be greater than 1.05. So the Higgs signal strength data disfavors kappa be greater than 1.05 at a 2 sigma confidence level. And this is a decoupling limit, which is kappa v equal to 1, kappa f equal to 1, and which corresponds to the alpha equal to 0, beta equal to 0. So this is the effect of the combined Higgs signal strength onto the parameter space of the Georgi-Machacek model as well as the extended Georgi-Machacek model. So now we try to look into the main observable, which is the mass parameters of the model. So we actually put the unitarity constraints bounded from below constraints are already included with the Senol unitarity constraints, and then include the Higgs signal strength, and finally we actually did a combined fit and look into the allowed parameter space from the combined fit. So this is the gray region, which is allowed from the all constraints. And you can also see from here that from going LL unitarity to NL unitarity, we actually geo parameter space gets much more constant. And then we put Higgs signal strength, which is kind less constant compared to the theory constraints over here. And finally, the gray region is the allowed parameter space when you impose all these constraints all together. So these actually show that the maximum mass splitting, which is between the different multiplets, this is the common mass, the degenerate mass of the 5-plet in the Georgi-Machacek model, and this M3 is the degenerate mass of the triplet. So if you look into the difference between these multiplets, you can see that mass splitting is at most 400 GeV from the combined fit. Yes. Sorry.
I just have a question.
Yes.
Would you expect this to change much if you took into account the oblique parameters?
Yeah. Well, actually, they are in a cubic tablet model scenario. If you look into the compare the NL unitarity constraints with the oblique parameter constraints, when you are in the same multiplex splitting, the oblique parameter actually do not do much. But when you go to the look into the splitting of different multiplets, your NL unitarity and oblique parameter could be actually competitive. But the complication here is that how to calculate oblique parameters in a Georgi-Machacek model or extended Georgi-Machacek model, or basically in the Higgs triplet scenarios. We are currently we have an ongoing work regarding this calculation of the oblique parameters, because as I already told, when you go from 3 level to 1 loop, your T parameter actually become divergent, because at the 3 level, you actually tune your parameters in such a way, you actually manipulate your Vk equal to Vj in such a way that your rho parameter becomes 1. But when you go into 1 loop, actually you kind of generate some new couplings, your sum of your new self-energy diagrams actually give you some infinite contribution. So in order to kill that infinity, you have to add new counter terms to your model. So the renormalization of this kind of models are not same as the standard model. So you have to basically renormalize the model again. You have to add some counter terms. Then only you can calculate the oblique parameters. So then you loop in how these oblique parameters can affect the parameter space. But as of now, I think from the Higgs tablet model comparison, I can say you that these oblique parameter bounds are very much competitive and sometimes weaker than the NL unitarity bounds. But once we actually calculate the oblique parameters for Higgs triplet models and we incorporate that in our feed, we can say like the final results.
Thank you.
So, Poulami, can you remind me in the Georgi-Machacek model, which one of the mass splittings is 0?
This is the Georgi-Machacek model parameter space. Here, there is no mass splitting 0. This is the Georgi-Machacek model. So this is your 5-plate mass and this singlet mass. But when you go from the Georgi-Machacek to extended Georgi-Machacek model, you do not have M5 anymore. All these candidates will have different mass. And then I will show you how the mass splitting. This is exactly the second slide. This is the mass difference, which was 0 in the Georgi-Machacek model, but now we have non-zero mass splitting. And this is the region that how much mass splitting you can expect in the extended Georgi-Machacek model. So again, we impose the LO unitarity, NL unitarity, and mixed signal strength, and combining all these constants, we can see that maximum mass difference within the same multiplet, which was 0 in the Georgi-Machacek case, is now at most as 210 GeV. And also in the Georgi-Machacek model, why we did that? Because we imposed NL unitarity constant, and you can see, and we have seen that this mass splitting 400 GeV we get, this is much more constant compared to the literature, in the previous literature, when people only impose LO unitarity. And of course, we also incorporate the latest Kanpur data, but since the theory constraints are much more strong in this panel, so the most significant contribution coming from the theory constraints, and this 400 GeV is much more constant what was there in the literature. So that's why we did that for the GM model, and the extended Georgi-Machacek model. This was done from the scratch, and we see that at most 210 GeV mass splitting one would expect from the extended Georgi-Machacek model. Then we actually calculate the flavor constant for the Georgi-Machacek and extended Georgi-Machacek model as well. So the flavor constant for the Georgi-Machacek model was already in the literature because it has one signature scalars that couple to fermions. So this is kind of a type 1 to SPM kind of scenario. So you can actually scale it in terms of the type 1 to SPM, and you can loop the constant of the flavor constant on the parameter space. But for the extended Georgi-Machacek model, these two signatures actually mixes, and because of that, you have two signature scalars that have coupling to the fermions. So the flavor sector gets more interesting for the extended Georgi-Machacek model. And if you calculate the constant coming from B to S gamma and R gamma, which is basically the ratio of this B to S plus D gamma plus B to CL mu, this is the R gamma. So if you calculate this Vs gamma or R gamma for the extended Georgi-Machacek model, you have two signature scalars coming into the loop, and if you calculate and loop into the parameter space, you can see that for the extended Georgi-Machacek model, the flavor constraints are less strong compared to the Georgi-Machacek model. Because if you have two signature scalars, so you have some parameter space to play with. So that actually gives you some freedom to open up the parameter space. So this is the and for the Georgi-Machacek model, what we did was we took the latest 2022 HFLAB results, and we see that we get a little modification over the results present in the literature. But the new findings are for the extended Georgi-Machacek model. Sorry. Yeah, so there was result for the Georgi-Machacek model. Logan and her collaborators did it, and we imposed the latest constant, and we see a little enhancement in terms of the V delta allowed region, and for the extended Georgi-Machacek model, this is the result. And also interestingly, we see that the low mass region is much more constant from the flavor data. And then the since recently in the LHC they are showing many excesses, and one most studied or interesting candidate is a 95 GeV scalar. So there are signatures of 95 GeV scalars going into gamma from the CMS and ATLAS, and also from the CMS 95 going to tau. There is a signal strength mentioned in this CMS analysis, and also long back there was also lap results for 95 going to VEVs. But in our work, we actually asked a much more fundamental question, that what are the parameter space allowed in the presence of a light BSM scalars between 90 to 100 GeV. So what we asked that if you have a light scalar in the mass 90 to 100 GeV, how large your other scalars can be in your theory. So in order to do that, we performed a global fit. We incorporate the theory constant, which are NL unitarity and bounded from below. We took the LHC data, which is the full run to Higgs signal strength. We incorporated the full heavy Higgs search as well as the light Higgs searches, and also incorporate the flavor constraints coming from the request gamma, because we have seen in the literature for the Georgi-Machacek model, this request gamma constraining map is more strong compared to the other physics observables. For example, VV by mixing or B2B. So as a case study, we incorporate the 95 GeV signal strength data, but our main question is that how large other masses can be if we have a light scalar in your theory. So we incorporated direct search for the extended Georgi-Machacek model for the first time. We incorporated the light Higgs searches as well as heavy Higgs searches, and we have we can see that this light region, light orange region, is as a result of the heavy Higgs searches. When you see that in the light mass region, the constraints from the heavy Higgs searches are weaker, but when you incorporate the light searches, which is incorporated in the all searches. So the all searches means heavy searches as well as light searches. We can see that the region gets much more constraints in the light mass area. So and this is mainly coming from the top detail, which is top going to H plus V. So these kind of details, from these details, this low mass regions gets constant. And also, I have already told that for the Georgi-Machacek model, we cannot have a light CP odd scalar because this CP odd scalar is degenerate with a single charge, and we have a lap bound of 80 GeV on the single charge. But in the extended Georgi-Machacek model, in principle, one can have light CP odd scalar. But it turns out that if you have one scalar fixed at 90 to 100 GeV, for example, if fixed at 95 GeV, then since in the extended Georgi-Machacek model, your CP odd mass can be written in terms of the other masses of the theory. So you can see that from the sampling, you cannot reach the allowed parameter space. Basically, it's the gray region from the sampling itself, and when you put unitarity constraint or the theory constraint on that allowed parameter space, you cannot actually reach less than 80 GeV compared to 80 GeV for the CP odd scalar. And then you put direct search, and finally all constraints means it has the theory, direct search, signal strength, and also the flavor constraint and all. And you can see that the all constant region, which is the blue region, cannot be less than for like 80 to 90 GeV. So for the CP odd scalar also, you cannot go less than that if you have a 95 GeV scalar in your theory. And also the limits on the triplet wave, which was from the full direct search, the heavy and light searches, we can see that the limit on the triplet wave is the 12 GeV for BSM masses less than 160 GeV, and which becomes 25 GeV when you have BSM masses greater than 160 GeV. So this was for the direct search result for the extended Georgi-Machacek model. And you can also see that the limit on the triplet wave are not dependent on the 95 GeV, or this is coming completely from the direct search limit and the flavor constraint. So the combined constraint putting on the Higgs on the triplet waves are robust, which are not dependent on the 95 GeV. So this is the results, which is 12 GeV for low masses and 25 GeV when you go to higher masses. And also, similarly, we look into the flavor versus direct search. Yes.
Sorry, could you go back one slide? So I didn't understand what is not allowing the white region in this bottom right plot?
Because in the extended Georgi-Machacek model, your CP odd scalar mass can be written in terms of other masses. So that is not an independent parameter in your model. So if you will fix one mass to be in between 90 to 100, that automatically forbids you to go from the gray region to the white region. So this is coming from the sampling itself. But if you set your other mass from 90 GeV to some another mass, then you could get some other parameter space. Because the CP odd mass is not an independent parameter. That you can write in terms of mass, other mass and couplings. The expression I do not have here, but we have in our paper. So that is a dependent expression of the CP odd. And then you put theory constant, you get much more constant, and then so on.
Okay,
But of course, these exercises depend on the where you fix your 95 GeV.
Yeah.
If you relax that, you can have in principle light CP odd scalar.
So how
But
large?
that we have not seen actually. That you are when you move from 90 GeV to some other masses, according to that you have your CP odd scalar. You can, I think we have a mass. No, here. Yeah. So you can have actually light masses. This is the This is the CP odd scalar. Ma, mass of the CP odd scalar. So you can see that this is the allowed parameter space when you do not have any 95 GeV. Okay. This is the full general parameter space. Just these are the constant imposing on the parameter space. So there you can see in principle you can go to the lower mass region.
So the reason I'm asking is that when you look at the contributions to G-2 of muon, light CP odd scalar is quite favorable because it will increase the standard model.
Yes.
So yeah, in that sense, that is quite important. But when you go for a very light pseudo-scalar, that is going to be kind of mediating these leptonic processes, doesn't your mu to E gamma bound become more stringent than B2S gamma? Because you mentioned that B2S gamma is much more limiting than mu to E gamma. Is that right?
Yes. In these, yeah. So this is the constant when this is the constant coming from the B physics observables. But when you look into some lepton flavor violating processes, there you do not see much constant because in Higgs triplet models your neutrino mass, which is you can write in terms of like U-cover times VEV. But here you have VEV is the order 1 parameter. So the U-cover coupling is very, very small. So you do not have much constant from the U-cover. Lepton flavor violating processes. Because you have order 1 VEV.
Yeah, because if that is the case, then your contribution to G-2 of muon is not going to be very large either. I mean,
yeah.
It's light, but yeah.
Yeah. True. Exactly right. So similarly, we look into the flavor versus direct search constant on the Georgi-Machacek model as well, because in the lower mass region, these two constants become competitive, which is flavor and direct search. So this is the Georgi-Machacek model where this green region is the allowed region from the theory bounds. This is the orange region is coming from the direct searches. This blue region is B2S gamma, which is less constant compared to the direct searches. And this blue region is the combined region from all constants altogether. So we have here the constants are I already mentioned that the latest data on heavy searches, light searches, and the H-club results of B2S gamma. So and also the theory, of course. And from this combined fit, the allowed region shows that we have 4 GeV at most wave limit for BSM scalar masses less than 160 GeV and 15 GeV when you have BSM mass scalars 160 GeV. And I also mentioned here that these limits do not depend on the 95 GeV scalar. So the result says that the direct search for stronger limits compared to the flavor data in both Georgi-Machacek model and extended Georgi-Machacek model.
May I ask a non-physics question? Well,
yes.
so HFLAV, does it incorporatable with HEPFIT?
Actually, we took the HFLAV data and we calculated the B2S expression and we put the experimental bounds on this B2S observable as a constant.
Okay, thank you.
So we did that. And this is the mass and mass difference then in the extended Georgi-Machacek model. So the mass difference between the same multiplets from the theory Higgs signal strength, heavy Higgs searches and flavor constant altogether. I think you can see the captions, right? The blue region is the combined fit allowed region, which says that the mass difference between same multiplet is 125 GeV for the extended Georgi-Machacek model. So which was 210 GeV before when we do not put direct search constants and flavor constants. So then when you go ahead and calculate the direct search constants and flavor constants, all together we see the mass difference between the same multiplets came out to 120 GeV. And mass difference between different multiplets is 250 GeV in the extended Georgi-Machacek model. Now, interestingly, since the mass difference is fixed to 120 GeV, if you have at most can be 120 GeV. So if you have 100 GeV scalar in your theory, and if you have some mass taking fixed, so the maximum allowed mass of your physical scalars in your theory is also get constant. So we see that if you have 95 GeV or a mass in between 90 to 100 GeV on theory, your heavy Higgs masses cannot exceed 600 GeV from the combined field. So, for example, if you in future, like we already have seen a 650 GeV excess, which is assumed as a 650 GeV. So, if you stay in the Georgi-Machacek model, and if you see a 650 GeV and 95 GeV both, that then your GeV model is not a viable model, or extended Georgi-Machacek model is also not.
So how dependent is that statement on the size of the couplings?
This is not, this does not depend any assumption on the couplings, because this is coming from putting all the theory bounds on the couplings. The only thing is that you have set one mass to be 100 GeV. So since your mass splitting is fixed, if you set one mass to be 100 GeV, so the maximum allowed mass of the other masses will get fixed also. So from that, if you say you have a 95 GeV scalar, then you cannot have a scalar which is above 600 GeV. So this was the finding.
Thank you. That's a very
yeah. So this is the mass and mass difference then in the Georgi-Machacek model. So we did that for the Georgi-Machacek model as well, and the heavy Higgs masses cannot exceed 530 GeV for the Georgi-Machacek model, and mass difference between different multiplets, because the same multiplets and degenerate in the Georgi-Machacek model. So the mass difference between different multiplets is of the order of 210 GeV. So here comes to the summary that will say that the minimal two-triplet extension of the standard model with rho equal to 1, which was assumed to the Georgi-Machacek, we say that the Georgi-Machacek model is not the minimal model, but the minimal model gives rise to the extended Georgi-Machacek model. But we do not assume any symmetry on the potential, but the minimum requirement to impose rho equal to 1 is considered there. So, and the quartic couplings in both the models are strongly constant from inner unitarity, we have seen, and also wave in the low mass region get most constant from the direct searches, we have seen already. And also in the presence of the light scalar in the mass range 90 to 100 GeV cannot have heavy Higgs mass greater than 600 GeV in both the models. So thank you very much, and these are my ongoing studies, which is as already Jasmine asked that how to incorporate bounds from electroweak precision observables. So these 6 triplet extensions are currently something we are looking at. And also interestingly, these both the Georgi-Machacek model and extended Georgi-Machacek model have trilinear couplings in the potential. which are not bounded from any theory constant as of now. So these are kind of, so we are actually currently calculating vacuum metastability analysis to put actually bounds on the trilinear couplings. Because we see that when people calculate electroweak phase transition in these models, the strength of the phase transition depends very much on the trilinear couplings. So if you put these couplings to be free parameters in your theory, so the analysis you are making is not very much robust. So currently we're trying to put bounds on the trilinear couplings and look into, then we'll look into the phase transition parameter space. That's one. Yeah. Thank you. I think I am on time. Yeah.
You are perfectly on time, yeah.
Oh,
Thank you so much. Yeah, wow.
thank you.
That was a lot to take in.
Yeah, and also I realized that I was switching like many times from Georgi-Machacek and extended Georgi-Machacek model. So that could be a bit confusing. So please ask me if something you get confused, because when we are calculating this, like we are writing this paper also, when we write two models separately, so it's sometimes get a bit confusing to tell that which are the results for which model.
But I quite like that on a lot of the slides you had the Georgi-Machacek model and extended one right next to each other. That was very useful to see.
Thank you. Thank you.
Good. So the floor is open for questions.
Yes, please.
Yeah, I'm gonna, maybe since nobody's spoken up yet, I'm gonna ask a question.
Yes.
So all of your extra scalars are coupling to fermions, right? So you don't have the option of a dark matter candidate.
Not on its own. You have to add something to the potential.
Okay, okay. And the direction of CP violation you haven't looked at yet.
We have not looked at it, but in the extended Georgi-Machacek model, there are CP violating phases.
Yeah.
Yes.
Yeah, I guess that would affect your I was going to say your vacuum metastability, but no, I mean, yeah,
Yes.
it would give you extra vacuum configurations. And that is very good. I mean, yeah, because as you said, a lot of people have been looking at electroweak phase transition in
Yes. In the Georgi-Machacek model, actually, people have looked in the electric phase transition, which was, of course, depend on the trilinear parameters, as I told. But since in the Georgi-Machacek model, there is no CP violating space, so people cannot actually, like, as much as I know that people cannot actually study electroweak baryogenesis. But in the extended Georgi-Machacek model, you can actually have phase transition as well as electroweak baryogenesis. But first we try to put bounds on the trilinear couplings, and then we move towards the phase transition study.
Yeah.
We expect that would change the parameter space significantly if we put bounds on the trilinear couplings. So one is that you can actually put unitarity bounds on the low energy regime also. That can put bounds on the trilinear couplings as well. But that is also a very much complicated calculation, because you cannot go to use the boson equivalence theorem. So you cannot write in terms of goldstones. So you have to write all the physical states and all the like 3-point vertices and compute the whole thing to calculate the low energy unitarity.
Maybe I can ask just one more elementary question, but back to your motivation. Just
yes.
Why were you? I mean, you picked an extension of the standard model with scalars, which was a vector, which was the spin 1 or of a SU2. I mean, you could have compared it with the spin 1/2 or spin 4. What was the motive? What was the reason? I suppose the reason for Georgi and Mondal to pick the spin 1 representation.
Yes, the scalar extension. So the scalar extension of the standard model, looking towards the scalar extension of the standard model, is because the origin of the electroweak symmetry. So if we see that the electroweak wave, we do not know whether it is coming from the doublet or it can come from the higher order multiplex as well.
But you could have picked for the higher order multiplet. You could, is what I'm referring to. You could have said, well, let me pick doublets and instead of extending it with doublets. You've extended it with triplets, which is spin 1 of SU2, or you could have extended it with spin 3/2 or spin 2. I think you had a spin 2 extension at the end.
Yes. You have on hyperchance. Oh, sorry. You have on hyperchance 0 and hyperchance 1 candidate in the Georgi-Machacek model.
But you could have extended it with other multiplets.
Yes.
Instead of just those. What was the reason for picking those ones? Is what I kind of missed at this stage.
The first thing was that the minimal extension one could think of is adding 1 doublet. So that was the well-known.
Adding 1 doublet would be the minimal thing one could do, or one could add 2 doublets.
Yes. And then if you stay,
do as well.
Yeah. And if you keep on adding 2 doublets, 3 doublets, and so on, you cannot actually get KV greater than 1. So since from the experiment we see that the base fit value for KV, it lies a value which is greater than 1. So in order to get that, you have to go to some higher multiplets where you have some doublets as scalar to compensate that. If you look into the unitarity.
So, but you skipped in the very end. You skipped the spin 3/2 multiplet. Would that not?
I didn't.
I think you mentioned a 5-plet at the end, which is
that was custodial multiplets. That were multiplets under the custodial symmetry, custodial SU2 symmetry. So in the Georgi-Machacek model, since you have a SU2 across SU2 or symmetry on the potential, after symmetry breaking, you have a custodial SU2. Under that custodial SU2, your physical scalars form multiplets. These are multiplets for
I see that they're extending it by a matrix model where as traceless matrix. So
I think what Denji was asking is why not 4-plets, 5-plets, and also why not multiplets of fermions? Is that right?
They could be scalars with in the 3/2 representation.
Yeah.
And they could even have SU2L left cross SU2 right. You could make the matrices.
Yeah. I think so. I mean, yeah. So this is the question about the original Georgi-Machacek model. But I'm guessing one of the motivations was the seesaw mechanism.
Yes, the seesaw mechanism is there in the extended Georgi-Machacek model as well. Like both the models you can have type of seesaw because you have a complex triplet in theory.
Yeah.
So for our case, the motivation was you look into the scalar extension of the standard model because you want to know the origin you do not know the origin of the electric symmetry rating. So there could be contribution from doublet as well as higher multiplets. Then you look into the experimental signatures. Where the Higgs couplings, standard model Higgs couplings, where they stay for the kappa V and kappa F parameters. When you see that this kappa V parameter is greater than 1, the base fit value, you automatically see that you cannot get in the minimal extension, which is the Higgs doublet model. So you go one step up and you look into the Higgs triplet models.
Okay, so I think I see the argument that you want to preserve SU2 left cross SU2 right symmetry, which is forcing you to have integer representations.
Yes, and that in the Georgi-Machacek model that automatically gives you a custodial symmetry.
Yeah,
which is also one thing.
Okay,
but
I have you now.
Yeah.
This rho parameter is the main guy.
Because
you can add as many as you want. The rho parameter does not change away from 1. With triplet, it does. So the Georgi-Machacek, I guess the brilliance of it was that they found a specific construction of the triplet extension that would not affect the rho parameter. If you go
yes.
For
so as a result, we see that the scalar physical scalars become mass degenerate. But in our model, what we asked was that is this the only possibility one can get custodial symmetric Higgs triplet extension? So it turns out that no, you do not need to impose this symmetry on the scalar potential in order to have the custodial symmetry, the SU2 cross SU2 symmetry. You can write down a general potential, you can perform the minimization, put the constraints over there, and as a result, your custodial symmetry is intact in the gate sector. which actually taking care of the W and Z boson mass expression for the rho parameter. But the scalar sector do not have that symmetry. So you do not have degenerate masses. And which is for the 2 Higgs tablet model as well. In the 2 Higgs tablet model, for the general potential, when you write lambda 4 and lambda 5, the usual notation, if you impose lambda 4 equal to lambda 5, your CP scalar and the signature scalar become degenerate. So that is kind of when actually you impose that symmetry on the scalar potential. But generally people do not do that. They put lambda 4 not equal to lambda 5, and as a result, your CP odd and signatures in the 2 Higgs tablet model are not degenerate. So this is exactly the same for the extended Georgi-Machacek model. You do not need that. That is the most general thing. Then you impose that symmetry on top of it, you will get degenerate masses, which was Georgi-Machacek model. But we try to look into the minimal case, where the custodial symmetry intact in the gauge sector, but not in the scalar sector. So that was the motivation.
Yeah, I think, and it's a UV complete theory as well. I guess if you were to look at guts, they would have 5 plets.
I want to look at run the RG parameters and look to how large the parameters can. Yeah.
Very good. Do we have other questions? Well, since I don't hear any more questions, I'm going to stop the recording.